So, next example. How do we know whether two propositions are equivalent? So it says here, two propositions P and Q are logically equivalent if they have exactly the same truth values for P and Q. Truth values for all cases. Below is a table. Let's take a look at an example of logically equivalent. Yeah. So these are examples of logically equivalent statements. And you have a name for each. This is known as the law of double negation. Not P is P. How are we going to explain this in simple terms? Not P is P. Okay, an example of not P is P is this statement. P, Fred. Not P, not Fred. An example of C? If you say enemy. Although this is not a very good equivalent for if you are not a friend, it doesn't always follow that you are already an enemy. But anyway, for simplicity's sake, let's say enemy is the negation of P. So, oftentimes you will hear people, politicians would say, the enemy of my enemy is my friend. Is this true? So the enemy, not of my enemy, is my friend. So this is the meaning, the enemy of my enemy is my friend. So that is an example showing your double negation. So let us check whether the following two propositions are logically equivalent. So according to the rule, they are logically equivalent if they have exactly the same truth value for all the cases. So just follow the rule for filling up the table. So these two will be given. You fill this up. So eto na siya. So, follow the rule. Next, take a look at this. And this. They have exactly the same values. So it follows that this one and this are logically equivalent. Next, laws of inference. Now, reasoning is the act of thinking about something in a logical or sensible way. There are two types of reasoning. Induction or inductive reasoning, which is drawing a general statement from particular cases. And deduction or deductive reasoning that deals with finding particular applications of a general statement. Most research studies use inductive reasoning, while deductive reasoning is widely used in mathematics. To give you an example of inductive reasoning, now this is an example of induction. 1 plus 3, 4. 3 plus 7, 10. 9 plus 13, 22. Oh, look. This is a particular case, particular. What is your conclusion? Let's take a look. These are odd numbers. This is another odd. And these are even numbers. So based on these particular cases, you can conclude that the sum of two odd numbers is even. So this is an example of an induction. What about deduction? Okay. You have a general statement. So let's say the general statement is the sum of the angles, interior angles of a triangle is 180 degrees. Okay, let's say for example, angle A, B, C. These are interior angles of triangle. Let's say A is 70 degrees. B is 40 degrees. So what is the measure of angle C? Since you know the general statement that the sum of the interior angles of triangle is 180, all you have to do is add these two, subtract it from 180. So this must be 70 degrees. So this is a general statement and this is a particular case. Deduction. Now more. It says here, mathematical reasoning involves thinking through given problems logically. But the question is, how does one know if something is logical? Well, the application of the laws of inference will ensure that one is reasoning logically. So you must be familiar with the different laws of inference. So that's how you will know whether your reasoning is logically correct. So there are 7 rules. 1, 2, 3, 4, 5, 6, 7 rules. This is the first one. We call this modus ponens, or simply affirming the hypothesis. It says here, if P is true, and P then Q is true, therefore Q. So P and P then Q, therefore Q. Affirming the hypothesis. The name is modus ponens. So each of these must be a tautology. So this is a tautology. But what is the proof for this? You have it in the previous example. So this is your modus ponens. P then Q and P therefore Q. Modus ponens. So that is a tautology. Now let's go back. Okay. So there are still others. Let's try this one. Identify what rule of inference is used by the following arguments. So, just study the structure, and then try to look for the pattern. Example. Here is an example. If it is sunny, then I will wash my clothes. It is sunny, therefore, I will wash my clothes. What rule of inference? Identify the parts. It is sunny. P. I will wash my clothes. Q. If and then, therefore, P, then Q. So, you will find it here. It is sunny. So, P. So, these two combine, N. The result is, therefore. So, this is an implication. Therefore. So, that way. Therefore, Q. I will wash my clothes. So, P then Q and P therefore Q. If you look at the pattern, this is modus ponens. Take a look at the second example. It is Wednesday. P. We have our math class. Q. Okay, P and Q. Therefore, it is Wednesday and so inverted B. We have our math class Q. P and Q. P, Q, and therefore P and Q. What is the pattern? So if you look at the table, where is that? Here. P, Q, therefore P and Q. P, Q, therefore. So that is conjunction. So that is an example of conjunction. The values of compound propositions in the study of bitwise operations, especially those students who are involved in the study of computer programming. They also make use of the operators like AND, OR, and exclusive OR. And they use the same concept. Here. We use binary digits. In the study of computer, they make use of binary digits, bits. So, they use 0 for false and 1 for true. So, let's take a look at the bit operations AND, OR, and exclusive OR. So, false, true, and remember, the conjunction AND will only be true if both are true. So, 1, 1, 1. True, true, true. Otherwise, false. So, 0, 0, 0. What about the inclusive OR? So, according to inclusive OR, it will only be false if both are false. 0 false, false, therefore false. Otherwise, it will be true. So 1, 1, 1. Exclusive OR will only be true if one is true and the other one is false. So 1 true, 1 false. Both false, false. Both true, false. False, true, therefore true. True, false, therefore true. So those are the rules. Now let us try to perform the bitwise operation. How do we get this? Okay, let's try the example here. Let us use the table. Example. Okay, let's take a look at the items here. Okay, so you are given 1, 1, 1, 0, 1, 0, 0. How many zeros do we have? 1, 1, 1, 0, 0. So that's given. And another one is 0, 1, 0. And 0, 1, 0, 0, 1, 0, 0, 1, 0. 0, 1, 0, 0, 1, 0, 1, 0. Yan. So, how do we get our end? Okay, for our end, you do it this way. So, the first one, 1, 0, 0, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 0, 1, 0. Okay, and it will only be true if both are true. Both are true. True. Otherwise, false na siya. True, false. False, 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 false. So that's the answer for M. Or letter B. Inclusive OR. It will be like this. 1, 0, 0, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 0, 1, 0. Inclusive OR. Okay. According to the inclusive OR table of values, your inclusive OR will only be false if both are false. Both are false. False, false, false. Otherwise, true. True, 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 true. Let me see. Both are false. Oh, here, there's another case. False, false, so this one must be false. There. Third example, exclusive OR. 1, 0, 0, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 0, 1, 0. Okay, exclusive OR. Exclusive OR means it will only be true if one is true and one is false. 1 true, 1 false. True. False, true. True. True, false. True. True, false. True. True, false, true. True. False, false, false. True, true, false. False, false, false. So that's the answer. 1, 1, 0, 1, 0, 1, 1, 0. So that ends your lesson 2. Just answer exercise L, that's 2.